What's up, everybody? This is Daniel. Welcome back to Code to Bare Metal. Glad you stuck around for another one. So today we're going to talk through a basic system design of a compiler that leverages an intermediate representation. So we're going to sort of talk about things at a high level, sort of take away each level of abstraction to the point where you understand what each component does at a high level, without talking too much about implementation details yet. In future videos, we're going to break down each component in much greater detail, talk about how you might build one. But nonetheless, I hope you really get something out of today and prepares you for what's in store. Without further ado, enjoy. Alright, so here today we're going to talk about what a modern compiler architecture might look like and how you might go about designing that if you were to make one yourself. So how I like to design software is I talk about my endpoints. So, first thinking about what is my initial input, and in our case, that is just a text file. And however that text is written is arbitrary. It can be in our custom syntax, but it doesn't have to be, because if it's not, the compiler itself will throw an error back to the user. So this is just simply a text file with anything in it. It can be empty, contain some random characters, whatever you want. And then you're going to take that text file through your compiler pipeline, and we're going to, in detail, define what exists along that compiler pipeline as we go, as we work our way in. And following that compiler pipeline, you want to output an assembly file. Again, pardon my awful handwriting. That assembly file should be in an assembly language that works for whatever architecture you're on. So if you're on an ARM machine, it should be an ARM. If you're on x86, it should be an x86, etc. And that assembly file should also contain all of the operating specific flags, the OS specific syscalls, etc. So this is very specific, right? Because if I build my compiler and I have it just target macOS Sequoia and an ARM architecture, that's not going to work if I send my compiler to somebody running Windows 11 on a Lenovo ThinkPad, right? So that's a problem. We don't want that level of specificity, at least in our case. So we want to abstract this process away. We want to abstract the process away of generating assembly code that is architecture specific, as well as the flags and syscalls that are OS specific. So we can do that with something called an intermediate representation, which we talked about in our last video. But essentially, IR is just a pseudo-assembly language that can be run through a just-in-time compiler, which is basically just a bytecode interpreter, like the JVM, that converts and executes our pseudo-assembly code to the specific assembly language instruction set that corresponds to the computer that we're running the compiler on, that also contains all of the OS specific flags and syscalls. So how do we get from that input text file to our desired output intermediate representation? So just to introduce a little bit of abbreviation syntax, I'm going to write something like this, and I'm just going to say X corresponds to my input text file and Y corresponds to that desired intermediate representation final output. So this, again, is abstract. So I'm going to define the first component along this pipeline, but the rest is going to remain abstract until we describe the rest. So I'm going to say, okay, the input text file is going to go through this thing called the lexer, which is what we're about to talk about. It's going to go through the rest of my pipeline, and then it's going to output Y. Let's talk about what I mean by tokens with an example. So let's say int a equals 45 is a valid grammatical definition of an integer variable, right? So I'm saying a equals 45. Okay, so this would be a valid input to my lexer, but I also need you to think a 45 semicolon int equals would also be a valid input to my lexer. Now, a later component of the compiler would throw an error because that's not valid grammar, but the lexer doesn't care, because it's simply breaking this down into discrete tokens, right? That are all valid. For this custom example, I'm going to define 5 tokens. And there's a number of ways to define tokens. In C++, you might do it as an enum, but again, there's other ways. There's a way to do this in Haskell, which we'll talk about later because that's kind of cool. But nonetheless, I'm going to say, okay, I'm going to define 5 tokens. So, and I'm going to define them as a pair of a token, like a token type, and then an optional value, which can hold none, and I'll explain why that's important, of some value. So we're going to talk through this example because I'm trying to abstract away valid grammar from what the lexer does. So here's what the output of that would look like. It's going to look something like this. It's going to look like a token identifier. We're actually going to do these as pairs, and it's going to hold the string A, right? Because I need to retain this information. Otherwise, when I get to later components, it sees token identifier, but how do I do anything with that? And then the same thing here. It's going to say, okay, token int literal, and then, apologies, I got to move over here, and I'm just going to store the value 45. Right? What's going on? There we go. Okay, 45. And then semicolon here. It's going to store token semicolon. But then it's not going to store anything because a semicolon is always a semicolon. If I give it a token semicolon, it knows that's a semicolon. So I don't need to store any associated value. I'm going to represent that with the empty set. That's not super correct, but just for sake of example, that's what we're going to do. Same thing with the int keyword up here. We're going to say token int keyword. And excuse the brevity, but I want to write as little as possible because I know my handwriting is not great. And again, I know an int keyword is always going to be an int keyword, so I don't need to store any associated value with that. And then lastly, I have that assignment, right? So you can guess, right? Token assignment. And, right, I need to store nothing with that because I know what an assignment operator is. There's no associated sort of ambiguity with that. So this is what the output of my lecture is, right? All I did was break this down into the smallest, most granular data format into individual tokens, and we'll talk about in a later video how we get there, but this is the output of the lexer. It's discrete tokens with associated values, and you can store that as an array, 2 adjacent arrays. Those are implementation details though, but you get the idea. We're breaking down into tokens and associated values. So now that we have our lexer, we can talk about the next components. So again, let's go back to that example, right? Int a equals 45 and a, 45 semicolon int equals, right? So now that we have our tokens, I want to validate that those tokens are in such an order that they match our defined grammatical structure. So, right, this is a valid token stream, but it's sort of meaningless, right? Unless for some reason I define my syntax that way, but we're not going to do that because it's funky and this just makes more sense, right? So this is a valid grammatical structure. So what I expect the order to be is a int keyword, an identifier, an assignment, an integer literal, and a semicolon. So what do we need to now validate the token order? To do this, we really need 2 components. So we need a data structure to store basically grammatical components of our language, and then we need an algorithm to construct those that data structure. So the data structure, I'm going to define as something called the abstract syntax tree, and we'll talk about what that means later, more in depth in a later video. And then a tree is just a bunch of nodes, right? So, and do not get this confused with a binary tree. This isn't binary. This is sort of a tree with where each node can have an abstract number of children, or an arbitrary number of children. And then, right, so then within this AST, we have AST nodes, which again, right, something like this. You've seen this all before in your data structure class, right? Something like that, where each of these are AST nodes. And then optimally, once we get this AST, we can then pass over it and generate our intermediate representation. So we're getting closer. So to generate the AST, we need something called a parser. And the parser is just an algorithm that takes in your input token stream from the lexer and outputs abstract syntax tree nodes that sort of, as you go, construct this abstract syntax tree. So we can refine our diagram a little bit further. So you have X, right? That's your input file. That goes into your lexer. That output then goes into your parser, which constructs your AST. And then, am I running out of room here? Yes, I am. So, right, we're just going to do something like that. And then that's going to get turned into your intermediate representation. So this is still abstract, but we're getting closer, right? To start, let's consider the following example. Just a very basic binary expression that adds two numbers. So, right, from our token stream, we know, okay, we're going to store a token int literal that has the value of 33. So, int literal 33. Then we're going to store the plus op token with nothing, right, because I know what that is. And then I'm going to store int literal 77. And then token semicolon. And that stores nothing. Okay, so with that, I need to say, okay, I'm going to allow basic binary expressions in my language. So I need to define an AST node that accepts binary expressions. So how I'm going to do that is we're gonna do this. So I'm going to say AST node binary. And what that is going to store is it's going to store a left expression. Oh, what's going on? Why are you not working? There we go. A right expression and an operator. With our example, 33 plus 77. How that's going to be stored is we're going to say, okay, here's what the subtree is going to look like. So we're going to have binary AST, and that's going to store three things. It's going to store the operator, which is just a plus assignment. And then the left expression is going to store 33. And then it's going to store 77. The nice thing, though, is we can make this infinitely recursive quite easily. And what I mean by that is consider this example. Very similar, but 33 plus 77 times 95. Well, the multiplication operator has higher precedence, right? Remember your PEMDAS than the addition operator. So what I want my eventual output here to be is AST binary. And this is going to have the multiplication operator. And on the left, it's going to have another AST binary of, there we go, plus, what was it, 33, 77, and then, what was it, 95, right? So, you can think about this. I could do this forever. I could have the binary expression contain two binary expressions in its left and right expression, and then those contain more and more and more, so this goes on forever. You're probably now asking the question, how do we get our lex tokens into this AST format and validate that the token stream is in such an order that it follows the rules imparted by this AST format? And we do that with the parser. So again, we're just going to do another example here. So let's consider an expression a equals 33 plus 77 times 95. Well, this is just the same expression we had above, so we know we're going to end up with a sort of nested binary AST node. And then we also have this over here, which is our assignment component. So what I would do here is I would define an AST node that represents a variable declaration. So it's very similar, or not variable declaration, variable definition. And all that's going to do is it's going to have type. It's going to have name or identifier. and then it's going to hold the expression, right? So how can the parser identify that this is going to be an integer definition? Well, the second I see an integer keyword token, well, it's either going to be a variable declaration or definition. So let's assume we don't have variable declarations and we just have definitions. The second I see a type keyword, okay, I'm going into a variable definition. So what I'm going to do is now I'm going to iterate over this token stream. And at this point, you can probably construct what that would look like, but it's just integer keyword, identifier, assignment, int literal, token plus, int literal, token multiplication, integer literal, semicolon, right? So how I'm going to construct this is I'm going to store, I know, okay, my type equals int, my identifier equals a, and then, right, but the nice thing is since I know I'm in a variable definition, I know exactly what a variable definition should look like. So in our syntax, I say int keyword, identifier, assignment, some expression, and then a semicolon. So I can put that logic into the parser. I can say, all right, I expect an integer keyword, I see it, I consume it, I go to the next token, I expect an identifier. If my next token is not an identifier, I can throw an error because that's not a valid grammatical structure. There needs to be an identifier here. If there is, then I go to the next token. If it's not an assignment operator, I throw an error. If it is, I consume it and I proceed. And then I call whatever would parse a literal expression, or in this case, a binary expression. And we'll talk about implementation details later, right? So then I'm going to parse this. If it doesn't match what I expect, we can throw an error because it's not matching the correct grammar. And then I expect a token semicolon. So the parser is really where you impart those grammatical details that didn't show up in our lexer, right? So back to it, what I'm going to do is then I'm going to store my expression as it's just a binary expression. So what this final AST node is going to look like is we're just going to go down here, is it's going to be a definition. So I'm going to have the identifier A, and then, right, so this is going to store type information, and then, right, equals, and then how did I define this? I said 33 plus 77 times 95. So times 95 plus, and then I'm just simplifying things a little bit, but you can refer to above if you want just a more detail. But again, right, this is similar. I'm saying, okay, this is a definition AST node, which is something I defined here, right? Sorry, I can't get a full circle there. And then I say, okay, I know it's A, I know it's equaling something, and then here's my expression, and then I sort of assert that there's going to be a semicolon at the end of here. As you go over your program, you're going to construct these AST nodes, and then what you'll eventually do is you're going to store sort of the top level one. So if we look back here, the top level AST node here is going to be an integer definition. All of this information here is contained within that definition as we defined it above here. So what I'm going to end up with is an array of AST nodes, right? And then that array essentially represents the abstract syntax tree for our program, because then you can think, okay, all the array represents is program, and then you have a bunch of top level AST nodes, right? As many as you want, extending from that, and then, right, these might have children, so on and so forth, right? You get the idea. So there's a lot of ways to do this, and we'll discuss some implementation in a future video when we really go into this in depth, but that's enough basic understanding for now. After we define our abstract syntax tree, we now need to go and construct our next component. So let's draw our diagram again. So we have X, which is just our input text file. It's going to feed through our lexer. Then that's going to go through our parser, which, remember, is generating our abstract syntax tree. And then I'm going to add a new component here called a Semantic Analyzer. And you can just think of that as a fancy type checker. And then here, right, this is still abstract. and then we are going to go to our intermediate representation final output. To familiarize you with this idea, let's consider two examples. So let's say bool. We're going to say, okay, I've allowed booleans in my language now. B equals 45 plus 33. So this is one component. And then we have another one where I say int z equals, 5. And int y equals z plus 7. This is just arbitrary, and this is another component, right? So this, under all of our common wisdom, is completely invalid. But nonetheless, our parser is okay constructing this as a variable definition AST node because it follows the structure we defined, right? You have a type, you have an identifier, you have an assignment token, and then you have some arbitrary expression. Whether that expression is of booleans, of integers, of floating point numbers, or whatever, the parser does not care. There's not enough sort of program level information to resolve that yet. So this is where we deal with that. And then we also need to consider this example. So we have some integer z, which is defined at 5. And just remember, this is all global scope now. We're not talking about scoping yet. And then I have this integer y is defined in terms of z, right? So here's the problem. Okay, it's happy. Z, great, some identifier. But we need to go resolve this type. So I need to somehow store variable definitions in a symbol table that also contain type information so that I can make sure that this is also an integer when putting it in this expression. Let's say this is also a boolean. This becomes invalid, right? Because z is now a boolean and y is just defined in terms of a boolean plus an integer, and that makes no sense. I don't yet want to talk about type resolution. We'll talk about that in a future video because that's a bit more of a complex idea and you need some pretty intricate components to deal with that, and I think that was sort of beyond the scope of what we're doing today. So let's ignore this, and we're just going to talk about this and how we could go about saying, yep, this doesn't work. So consider this, right? Bool b equals 45 plus 33. So that's going to construct the following AST node. So it's going to have a definition of type boolean stored in B, right? And then equals. Sorry, we're going to run out of room, so we're just going to go on to the next page here. And that's going to say, or nope, pardon me, plus 45, 33. So it's going to grab this from that top level array that represents our abstract syntax tree. Remember we talked about that a little bit earlier. And it's going to look at this thing, and it's going to go in this direction. So first, it's going to look at this binary expression. We know integer literals are completely valid, right? Because they're just integer literals. There's no way for that to be an invalid expression. Now, there is a way for this binary expression to be invalid. So we're going to say, okay, we're going to look at 45 plus 33 now. Okay, well, this is a valid binary expression, and we're going to resolve that type to integer. So now I know this binary expression holds the type integer. It has these two sub-expressions, and it uses the addition operator. So this is resolved. This is okay. It's happy because these are both of the same type. Now it's going to look at essentially the rest of it. So we're saying, okay, we want to assign 45 plus 33 into B, but B is a Boolean. So since we've resolved the type of this as an integer and B is a Boolean, it's going to say, well, these types are incompatible, so now I'm going to throw an error. And it's really that simple. You're just sort of walking your tree bottom up and validating that all of your types match. Now we have our type checked AST. So it's been completely validated and is now ready to be converted into CPU executable code. So now we're going to put in the last component of our pipeline, and it's not going to be abstract anymore. Besides, of course, component implementation, but the pipeline itself no longer has any ambiguous components. We know exactly what we need to do. So, right, we have X, that feeds into our lexer, that feeds into our parser, which then in turn feeds into our semantic analysis, an analyzer. We should write that semantic analysis. This is going to go into our Codegen, and then this is going to go into y. And this is no longer abstract because Codegen is going to take your semantically analyzed AST, right, basically glorified type checker, and convert it into your intermediate representation. And the IR is our target, so this is not abstract anymore. As good programmers, we've defined each AST node to be distinct and unique, so we can call explicit codegen functions on each AST nodes, thus removing any ambiguity and ensuring correctness of the output, although LLVM provides other ways to enforce that, but nonetheless, it's useful. So to generate IR, what we're going to do is we're going to make another pass over our AST, starting at the leaf nodes, going bottom up, and generating IR for them. As we've decided that we're using the LLVM, to do this, we're going to make use of 3 core LLVM APIs. So first is something called the context. And all that is a global bookkeeper for all LLVM objects within a singular thread of execution. So it ensures that all memory is allocated and deallocated correctly. It holds all of the information about LLVM types, constants, and other metadata related to the overall program, and provides the infrastructure to ensure type consistency and IR correctness. Next is something called the module. Let's write that down. And what the module is something that's generally associated with a singular source file that holds all the functions, variables, and IR code we generate, and in addition provides the infrastructure to operate on that IR later during optimization passes. The module depends on the context, and multiple modules can depend on the same context. Think of it as a singular unit of compilation. Lastly is something called the IR builder, which is what actually allows us to insert LLVM instructions into a module. So it holds information like the insertion point for instructions, which is important for control flow when we have to deal with function definitions, calls, conditionals, loops, among other constructs. Then validates that the generated LLVM instructions are correct, thus abstracting that away for us as well. There's so much going on here, and I'm still very much in the learning stage of using the LLVM. I think I always will be, but at some point in the near future, we're going to begin to explore the LLVM in great detail. But first, I wanted to get us to a point where we have a solid understanding of how we can get to the point where we're ready to generate LLVM IR. So first, we're going to talk through the lexer, the AST, the parser, and the semantic analyzer in much greater detail than we did today. The last thing I'd like to talk about is what can happen after Codegen. So once we get to Y, remember that's our IR, we can go to Z, and I'm going to say Z is the assembly code that our computer can run. So to get to Z, and we're not going to talk as much about this to start, but there's a lot to unravel here, and we'll explore it later on once we get through more of the compiler front end. What you can do is you can take this IR, so Y, and you can loop back to Y by running optimization passes. And how that works is there's often going to be redundant instructions or unneeded instructions that can be removed in your IR that follow common patterns, right? Because your language at the end of the day is a pattern. So here's a very simple example. Consider int a equals 0 plus 44. Well, that 0 plus is not very helpful. That's just extra information. That's adding an extra add instruction to the IR. Why do I need to retain that? Well, one of the optimization passes you can do is if I see a 0 plus, just remove that instruction altogether, and it's no longer going to be a part of our final executable. Another thing you can do is you can convert the LLVM to another intermediate representation. If, say, LLVM isn't supported on the CPU architecture you want to run on, but another intermediate representation is. So that is something that compiler engineers do in the real world. So that's something to consider. But then, following all of that, we want to get our IR to an executable that runs on our machine. So you're going to run it through a just-in-time compiler. So, right, you're going to take Y, right, you're going to do your optimization passes, you're going to run it through the just-in-time compiler, and then you're going to get the output executable. So LLVM provides the orc just-in-time compiler, but you can also write your own, which makes it really easy. The OrcJIT makes it really easy to ship your language and not make you worry too much about machine-specific details, which is super convenient, and that's really one of the primary reasons we make use of IR. So once we go through the just-in-time compiler, we have an executable, and now we can run our code. All right, I know that was a lot today, a lot of information. I tried my best to condense it as much as I can, but I know this one's going to end up being about a half an hour, but I'm okay with that. I hope you learned something about system design, about the architecture of modern compilers, maybe learn some new interesting use case of the tree data structure. I don't know. I just hope you got something out of this and are excited for us to dive deeper into each component. So next week or in 2 weeks probably, we're gonna take a deep dive into the lexer. We're gonna talk in greater detail about each individual component of that lexer, not just what it does. And then we're gonna implement one. So we're gonna do one in C++, I think. Because, you're working with the LLVM, you're probably working in C++, and I think everybody should know some C++ anyway. So we're going to do it there. And then we're also going to do one in Haskell, because I've been having some fun with Haskell. Lexing, parsing, it's all just complicated pattern matching, right? And functional programming languages are really designed for that. So if you're interested, you can stick around for that. In that video, I'm going to give a simple sort of toy language that we want to lex, and maybe we'll take that toy language through the entire pipeline as we go. Who knows? But we're going to start. I'm going to say, okay, go lex this in whatever language you want, and then you can come back and I'll have a couple of solutions that I implement myself and talk you through, and hopefully you'll get something interesting out of that too, and a bit of a deeper dive into what goes on in lexical analysis. After that, we'll do something similar with parsing and AST, as well as semantic analysis, and then that's when we'll really get to start talking about LLVM. I really want to get you all to a place where you're comfortable with what you need to get to LLVM, because I think it would be a mistake for us to just jump into that right away without understanding what needs to happen before that. So I just wanted to thank my wonderful fiance Hannah for the images of me. I have a little one of her right here. She drew one as well, so I could give a shout out. And I look forward to doing more of this. As always, please leave comments, subscribe, like the video, and leave any feedback or suggestions. I really enjoyed interacting with you all after the last video. So yeah, let's keep it going. Thank you again.